Thanks a lot, and good afternoon, everybody. Except for two people back there, it's John Bond there and Martin there, that kept me so busy last night with scientific discussions that please wake me up if I fall asleep. All right, so actually, just to make a short plan of my talk, I would like to spend few words about lithium chromium mixtures and especially lithium 6 chromium 53 Fermi mixtures. My motivation originally and let's say later motivations that came from Michael group, and I will spend few words skipping technical details on how we do it. And then I will spend some time telling you about kind of recent results in a joint publication we had with Michael's team concerning production and characterization of a high phase space density gas of paramagnetic lithium chromium Feshbach timers. And I would like just to conclude giving you some news from our lab concerning other isotopic combinations of lithium and chromium, and also some recent exploration of chromium-2 system. All right. So my initial motivation concerning lithium chromium has nothing to do with polar molecules at all. And the interest of this Fermi mixture for me is just connected with a very peculiar mass ratio that is about 8.8, which falls extremely close to two interesting mass ratios predicted in the context of few body physics that are 8.2 and 8.9, essentially, that are the critical mass ratios for trimers and tetramers with a non-Efimovian character that are predicted to exist. Has never been investigated in whatever physical system so far, but what I kind of like of these cluster states, that unlike Efimov clusters, they are supposed to be collisionally stable. And I mean, although I must confess part of my permanent position may come also because of study of Efimov states in the past, I would dream of seeing, let's say, weakly bound cluster states that are collisionally stable. And with this, you could then explore new impurity problems, especially in the context of light impurity atoms, and associated with a kind of rich, novel kind of quasi-particles. You could have also kind of exotic superfluid and normal states like FFLO or trimer Fermi gases, or what is called nowadays quartet superfluids. Yeah, and all this is kind of intriguing to me because it kind of make some strong connections to two-dimensional TMD materials and stuff like this. So I mean, that was the original plan, yeah. But out of lithium chromium, it's also that this is not a bialkali mixture because we combine an alkali atom with a transition metal element. So spin 1/2 with spin equal 3, and actually already some years ago, Michael contacted us telling us that indeed in the ground state, lithium chromium dimer was expected to exhibit a fairly large electric dipole moment on top of a relatively large spin of 5/2. And I mean, I don't need to explain you why. I mean, you know probably much better than me why dealing with ultra-cold paramagnetic polar molecule species could be interesting. All right, so in practice, that's not so easy experimentally, because lithium-6 we know very, very well, and you can do whatever you want to lithium-6 and it will anyway work, and that's fantastic. But on the other hand, chromium was something like a nasty species, although being pioneered by Tilman Fao back something like 20 years ago or more, and especially chromium 53, which is the only fermionic isotope of chromium, was essentially unexplored except from brave guys in Paris, in the group of Bruno Labourte, with, however, not so exciting numbers concerning atoms loaded into the MOT at fairly high temperatures. And I mean, they could achieve kind of Fermi degeneracy with something like 500 atoms back in 2015 or so. So not really encouraging. However, we were kind of brave, and especially I was very lucky to have very brave students and postdocs. And to make a very long story short, we followed essentially a null optical procedure that we were developing already back then for lithium potassium mixtures in Innsbruck with Rudi Grimm, and essentially copy pasted it, adapting it to this chromium nasty species. But as a matter of fact, this works fairly well, even better than lithium potassium in Innsbruck nowadays. And I mean, out of 13 overall 13-second duty cycle, we can get doubly degenerate mixtures of lithium and chromium with fairly high numbers. Yeah, something like MOT numbers of the original MOT of chromium 53 now are kind of at a quarter of Fermi temperature. Actually, let's say, being a completely unexplored system, we needed to know what kind of Feshbach resonances and scattering properties this mixture has. So it took us something like 1.5 years to look into Feshbach resonances. We indeed found something like 55 or so Feshbach resonances in different spin combinations of the lithium chromium mixture. And actually, the interesting thing of lithium chromium is that although you may think of chromium like very resembling magnetic lanthanides, at the end of the day, the chromium element looks much more similar to a kind of complicated alkali rather than to a very complicated magnetic lanthanide. And especially the spectrum is not chaotic. And indeed, like for bialkalis, lithium chromium dimer has two channels only, which play, let's say, the role of singlet and triplet for bialkalis, and in our case they are sextet and octet. And thanks to long and fruitful collaboration with Andrea Simoni in Rennes, we could build up an assignment and a quantum collisional model for lithium chromium, which works kind of beautifully. So as a matter of fact, out of this big thing, the interesting thing to take in mind are that at low field, we have very broad resonances, but these are only P-wave resonances. And could be some of those very interesting resonances, but I won't spend any time on that. And concerning S-wave resonances, indeed, we have also some relatively similar, let's say, in terms of magnetic field widths and effective range parameter to the ones we were exploring in lithium potassium mixtures. The problem being, however, that these are, so kind of the broadest S-wave resonances are located at something like 1400, 1500 Gauss, and they are only half a Gauss wide. So can we really exploit them? And also there, thanks to some efforts in stabilizing the field at these bias fields down to 1 or 2 milligauss over tenths of millisecond, which was kind of an achievement. We could indeed exploit them, and here I'm just showing you quickly the result of a characterization we made just to pinpoint and study elastic and inelastic rates of atomic scattering close to the resonance pole. And just forget about how we do. In practice, the interesting thing here is that we can indeed access with a few milligauss step size the resonant regime with this new mixture, and both rates are matching the expected trends. And what is nice is that as we deal with a Fermi-Fermi mixture, although close to a narrow Feshbach resonance, we have relatively good to-bad collision ratio exceeding 200 for, let's say, the case of relatively high dense and relatively cold sample, which is good. So basically, out of this, we then just moved and tried to associate dimers. And what is nice here, what we were essentially copy-pasting what was done back then for many bialkali systems. We were just looking at magneto-association efficiency as a function of the ramp speed with which we cross the resonance. And in practice, we find, I mean, we can analyze our data and find good agreement with theoretical expectation based on a Landau-Zinner model. But besides details, what I want to point out is that we can get fairly high efficiency, exceeding 50%, and 50K dimers can be formed at relatively high phase space densities of about 0.2, benefiting from the fact that, let's say, these are bosonic molecules, but unlike sodium cesium case, these are made by two fermions. And fermions in the strongly interacting regime are nice because they are stable. Yeah, so we can afford to make very, very long magnetic field and slow magnetic field sweeps that do not perturb the system or limit the lifetime. Yeah. And actually, one thing we were also looking into was indeed to characterize the magnetic moment of these Feshbach dimers. And the way we did was similar to what also Rudiger group made with dysprosium potassium dimers. So we were just looking at, let's say, expansion of atoms and dimers into a magnetic field gradient, make a sort of Stern-Gerlach experiment, and then out of the tracing of the trajectory of lithium, chromium, and lithium-chromium dimers, we could determine the lithium-chromium magnetic moment as a function of the magnetic field detuning. And there it kind of fits well with what you would expect just based on effective range theory. And let's say, essentially, we can observe, although the resonance is fairly narrow, a kind of transition from, let's say, a regime where the magnetic moment of the dimers is essentially coincident with the open channel magnetic moment, that is 7 mu b, down to large detunings of a few hundred milligauss from the resonance pole to something like 5 mu b, which corresponds to the closed channel dimer magnetic moment. And out of this, let's say, besides being happy that we could tune, let's say, magnetic field and stabilize the field down to this level at a bias of 1414 Gauss, what made us happy is that indeed these dimers are paramagnetic, and as a matter of fact, they are, let's say, the last vibrational rotationless level of the sextet ground state potential. Okay. And I have absolutely no time to discuss here, but we also had some interesting determination of the so-called open channel fraction of these Feshbach timers through a very simple optical scheme, thanks to Alessio Chamei, who is really the guy of lithium chromium molecules, I would say, and my colleague in the lab. And here I just want to spend few words concerning this lithium chromium collisional stability, and let's say basically focusing on atom dimer collisions. Yeah, and basically we are dealing with these Feshbach timers that are, let's say, highly excited. So as soon as let's say a particle, like for instance lithium, collides with a dimer, what it can happen is that simply they make some vibrational quenching, and basically you have a huge release of kinetic energy and essentially losses. So if the dimers are kind of far from the resonance pole, this kind of inelastic rate is on the order typically of, let's say, 10 to the minus 10, and it can be quite easily be shown that this scales like essentially van der Waals length over reduced mass of atom dimer pair. However, because let's say lithium is identical to one of the two atoms that makes the dimer, and these are fermions, you expect indeed that if we go closer and closer to the Feshbach resonance, and where basically the dimers realize at short range to be made of two atoms, essentially, you expect that these inelastic losses are going to be suppressed, and eventually suppressed substantially. So we did this kind of experiment, and first we had a look at what happens as a function of the magnetic field detuning to, let's say, lithium dimer collisions with the lithium atoms being prepared in a non-resonance state. So let's say this resonance is, say, associated with lithium-1, chromium-1 state combination. Here we were looking at inelastic losses between lithium-2 and these lithium-1, chromium-1 dimers. And as you can see, this is the empty symbols. They are essentially flat, and no matter where we tune the magnetic field, we see a fairly high loss rate. On the other hand, if we just keep the lithium atoms in the resonance state, so lithium in the identical state of the lithium atom composing the dimer, we indeed see that there is a very strong suppression as we approach the Feshbach resonance, in spite of the fact that this resonance is really narrow. Yeah, and this is kind of nice because let's say we can lift up the lifetime from a few milliseconds far from resonance up to more than 100 milliseconds, very close to resonance, which is something like nice because we are already at a very decent phase space density with this dimer gas. So just a very little short sympathetic or evaporative cooling stage could allow us to get a Bose-Einstein condensate of Feshbach timers. And clearly, I mean, we have heard, and I learned a lot during these talks in the past days, that you can have shielding and, let's say, very nice tricks to evaporate in the ground state these molecules. On the other hand, if you could get rid of this evaporative cooling stage in the ground state and just start with, let's say, a Bose-Einstein condensate or a deeply degenerate Fermi gas of Feshbach dimers and adiabatically bring down to the ground state, that would be cute. And as a matter of fact, let's say, unfortunately, lithium-2 dimer is probably the most useless one, but I mean, I guess if you had some interest in dealing with lithium-2 dimers, that would be the right way. I mean, you just sit on top of the resonance, evaporate, get a condensate of Feshbach dimers, and only afterwards you can transfer. Yeah. Good. Just to conclude this part, it's something like prospect for ground state and deeply bound states. So thanks to Michael and collaborators, we have quite a bit of information concerning the lithium chromium system. Now just take in mind these 16 and 46 that are the number of vibrational levels foreseen by Michael team. It overall looks like lithium chromium being fairly similar to CAF to some extent, and actually one interesting thing that Michael and co-workers could find out or predict is that already for relatively weakly bound states, electric dipole moment exceeding 1 dBi could be there, which is kind of interesting. And also, because of the fact that our Feshbach timers are already purely sextet in character, we expect a quite efficient stirrup scheme to be possible, like a sextet to sextet stirrup scheme, analogous to the one by Kai Dickmann in the case of potassium lithium, that for bialkali means singlet to singlet stirrup. Good. Just in the last 3 minutes, let me just flash a few new things we had in the last months, waiting for our TISAF laser, with which we plan to do spectroscopy and identify, let's say, the stirrup lights in the experiment. And let me just once again emphasize that these achievements I'm going to flash now are essentially due to this guy up there, together with my PhD student Beatrice. And yeah, basically playing a bit with a super simple but smart double optical dipole trap loading of lithium, plus upgrading the laser setup of chromium, we could essentially achieve, let's say, substantially higher numbers of lithium-6 Fermi gases. I mean, getting also some benefit for the chromium temperature and atom number. And not only this, but we could also recently Bose condense also chromium-52, which was Tillman initial dipolar gas. And nicely, we also could Bose condense chromium-50, yeah, which is something like a pure abundant bosonic isotope of chromium. And obviously, with 2 new Fermi Bose mixtures and potentially weakly dipolar new BEC, clearly we were asking what are the scattering properties, Feshbach resonances, can we make lithium chromium fermionic molecules, and what about chromium-chromium? So in practice, let's say we just made some Feshbach resonance search, now targeted on lithium-6 chromium-50 and lithium-6 chromium-52, benefiting, however, from the knowledge we already had from our past spectroscopy on lithium-6 chromium-53. And out of this search, we essentially found out that all lithium-chromium combinations have very similar scattering properties. From asymptotic bound state model calculations, we can fairly precisely guess what are the sextet and octet scattering lengths of the different combinations. And actually, we are very proud that our Michael calculations were perfectly matching our findings. So congratulations, I think we are proud of you. And let's say last thing is we were also trying very briefly to see whether we could associate molecules of from this Fermi boson mixture, and the answer is yes, and we can associate actually fairly high number of fermionic lithium chromium molecules, which is also nice, and it's a promising starting point to make also Fermi gases of these paramagnetic dimers. Very last thing, we also looked into chromium that was something like investigated long ago by Tillman with only the chromium 52 isotope. We have identified some chromium 50 and chromium 53 homonuclear Feshbach resonances, and out of this, I think we are pretty confident we can fix the high spin potential. And if our current assignment, which is still preliminary and to be tested, is correct, indeed we can fix the number of vibrational levels of all 6, 4, and 2 spin potentials. And last but not least, we also could have identified the spin exchange resonance between chromium 1 and chromium 2 of the fermionic chromium, which looks like a relatively broad Feshbach resonance, something like 4 Gauss wide, which could allow us to make a sort of BCS-BEC crossover like of gas with a weakly dipolar character. And so to conclude, next we are going to look for spectroscopy and implement stirrup transfer to deeply bound levels. And we are kind of excited because this new Fermi boson mixture and also chromium 53 mixtures could be very interesting, let's say, also in the atomic perspective. And last but not least, let me emphasize that chromium-based diatomics in general are kind of appearing more and more like a promising species for a lot of application. And I think you are going to listen more about this in the next section, next session by Adam Kozas. And with this, thanks a lot for your attention. Yes.
Thank you, Matteo, for your talk. Any questions from the audience? John Bone over there.
But that's Martin,
Martin.
right?
Oh, yeah, sorry, Martin. Martin.
So this is wonderful stuff. May I ask about the chromium
No.
Feshbach resonances? Okay.
Sure.
No, you say now, based on these observations, you've nailed down the potentials for the S equal 2, 4, and 6. But there are others.
Yeah.
I forget how many. So is this sufficient? You need only those 3 to account for all the observed resonances?
That's let's say it's a good question. Let's say no. I mean, it looks like so far the only funny missing resonance which we don't understand is this kind of broad feature about 280 Gauss in the fermionic chromium mixture. Yeah, all the others seem to be compatibly assigned, just playing with these 3 potentials essentially.
All right, interesting. Thank you.
More questions?
very exciting to see this all this
Thank you, Chen.
progress. So I have a question regarding that. You can see these stable molecules with a pretty significant fraction creating from degenerate Fermi SO2 species. And do you see the fraction and is just coming from collision or is coming from thermalization? Because it's a longer lifetime to see the thermalization at the molecules.
Let's say, if I, let me just go back. Let's say, I cannot really tell you anything about the fermionic system because we have just blindly applied what we were doing for the Fermi-Fermi mixture and just checked if it was working. It was working, but we have not characterized yet anything. Concerning the Fermi-Fermi case, here I think it's quite a funny thing because let's say we have spent months and months getting very, very short lifetimes, irrespective of what we did, finding ultimately that the problem was just the wavelength of our trapping beam. Yeah. In practice, if we get rid of lithium, which is the most nasty colliding partner for the molecules, we have so far not managed to observe any inelastic chromium dimer or dimer-dimer collision somehow. And losses, say, this kind of lifetime here is most likely mainly dominated by, let's say, spilling out dimers from the trap, because after removing the leftover atoms, we get some sloshing and breathing and some excitation that we have to put more and better under control. But let's say it's an interesting thing, right?
I think we should. Yeah, you have a quick question or? Yeah,
Just a quick comment. And then it looks like you are in very good position. If you have a more chromium and mixed with the dimer, the system can thermalize.
That's the way to go.
Even higher,
absolutely.
Dimer fraction.
Yes.
And even very close to degenerate.
Absolutely.
Okay, we should move on. So thanks again, Matteo.
Welcome.